And so yes, this will be a two-part lectures about Khovanov homology. So today I would like to introduce to you Khovanov homology for links, as was introduced by Ozsváth, Rasmussen and Szabó in 2007, I think, and develop a bit the tools you need to work, I would say, work correctly with it. And then next week, I will talk about my joint work with Krzysztof Putyra on how to extend this Khovanov homology from links to tangles. So I will assume that maybe not all of you are already well acquainted with Khovanov homology. So I will first try to maybe remind you or maybe introduce to you quickly how Khovanov homology works. All right. So what you do is you first start with the diagram of a link, L, and say this link has k crossings. Oh, yes, thank you, Dror. Yes, the slides are available online on my website. Here. So that it's very easy to get them. Okay, so you start with a link and k crossings. And then for each crossings in your link diagram, so you should imagine here, for example, that your crossing is inside a big diagram. You choose a way to resolve it. You can do a zero resolution. So what it means is you replace your crossing here by this smoothing here locally. So you keep the whole diagram the same except at the level of the crossing. Or you can take a one resolution and you do it like this. Okay, and so given a k upper of 0 or 1, you get a resolved link diagram by replacing the IM crossing by a 0 resolution if the IM element here is 0, or 1 resolution if it is 1. And so if you do this, you get a resolved link diagram, which consists only of a disjoint union of circles, basically. And now here is the magic formula due to Kaufman. If you do the sum over all these choices of resolution of -1 power the number of one resolution in your state times these polynomials here in Q power the number of components in your resolved link diagram. That is the number of circles. And if you do this, you will get some nice Laurent polynomial in a variable Q. And it appears that this polynomial is exactly the joint polynomial. Well, maybe you have to renormalization, but don't worry too much about it. And this joint polynomial is famous to be known a link invariant introduced by Vaughan Jones in the middle 80s. And so Khovanov homology is about categorifying this picture. So here categorifying means that we want to replace this formula here by a complex of vector space where you can interpret this minus sign as some homological degree and this Q as some grading. So what you want is really complex of graded vector space whose graded Euler characteristic is this guy. So somehow this formula already tell you the space you want, because you know that somehow for each state here, you will get a vector space whose dimension is basically 2 to the power of circles. But because you want a complex, you want some map between these spaces. And so we need now to reconstruct these maps. And it appears that we can already start by thinking in terms of topology and try to add maps in the picture above here. So what we want are maps between our different resolution of the link. So you want a way to go from, say, a 0 resolution to a 1 resolution. And so you're looking for maps between closed one manifold. And one way to do that is by using cobordism. So what we can do is construct cobordism between our different link resolution. Whenever you have, say, a 0 resolution, you can go from there to a 1 resolution by just putting a saddle point over here. So again, you need to think of this diagram here inside a huge link diagram, resolved link diagram, so a huge collection of circles. And everywhere you just take the cobordism given by the identity, except there where you put a saddle like this. And you can see that a saddle like this goes from 2 horizontal line to 2 vertical line. And if you do this for everywhere you have a 0 resolution, then you will end up with some kind of huge cube of resolution where the edges are cobordism. So it looks like something like this. Here is the trefoil knot. You have 3 crossings. First, you start by putting a 0 resolution for each of the 3 crossings, so you get a picture like this. And then for each of these crossings, you can choose to go to a 1 resolution. For example, here, this is the first crossing. And if you do a 1 resolution, you end up here. Here the second, etc. Okay, so this picture was from drawer. Apparently, someone told me that this picture was from Barnatan. So that's where I took it. So thank you, Barnatan, for your picture. Okay, so if you do that, you get this huge cube. And each of the faces of this cube, okay, and if you look at one face of this cube, and you follow one path here, what you do is you first put, for example, a saddle on this point here, and then a saddle on this point here. Or first on this point, and then on this point. So you are putting saddles over the 2 same crossings, but there will be a different height because you are stacking cobordism. Hopefully, if you consider cobordism up to equivalence given by homeomorphism that fix the boundaries, then these 2 paths here are exactly the same because you can just exchange the height of the saddles in your cobordism. And then you get a commutative cube. A commutative cube. But what we want is really a complex where this should be like in homological degree 0. This should be in the homological degree 1, and this is in the homological degree 2, and this is in the homological degree 3, where the homological degree corresponds on the number of 1 resolution in order to be to match with the formula here, basically. So if you want to turn this into a complex, we need anticommutative faces. So we need to throw in some signs. But you cannot throw some signs in this category of cobordism. So what you need to do with some algebra trick, you need to linearize the category of cobordism. So let me write for K-cop the category where objects are formal direct sum of closed 1 manifolds, and the home space are given by formal K-linear combination of cobordism between these 1 manifolds. And so now if you do this, you can just put the signs you want in your cube to make it anticommutative. There are some combinatorial rules to do that that are not too hard. Another maybe better way to think about it is that your cube is some kind of iterated mapping cone. If you're familiar with homological algebra, then it is something very natural to do. And then this gives you a complex. But of course, here there is no chances that this complex is a link invariant, even with homotopy type or something. So so you need an extra ingredient. And this extra ingredient should send, in order to match with the state sum formula that I gave you before, should send like a circle to some 2-dimensional vector space. So what we do is you apply some TQFT given by the Frobenius algebra kx on x squared. This is a 2-dimensional algebra, so it will send a circle to a 2-dimensional vector space. And if you don't know what's a TQFT, well, it simply means that it is a functor from the category of cobordism to the category of vector space. Okay, and so you can, because it is a TQFT, you can apply it basically on your complex here, and you get a complex of vector space. And now the main result of Khovanov.
We have a question from Jin. Can the cube picture be done for a general skein algebra?
I think I'm not sure. Probably someone can answer that. Yes. Okay, and so the main result of Khovanov somehow is that the homotopy type of the complex you get after applying this TQFT on your complex of cobordism is an invariant of links. And of course, but because of the way we constructed this complex, this hereditary characteristic is exactly the joint polynomial. And now maybe you are thinking, but why should I care? Why is it interesting to do this more complicated construction? Well, a first answer is that it gives you a stronger invariant than the joint polynomial, because you have a lot more information there. And also, now you are not playing with polynomials, but you are playing with spaces. And so one thing that you can do is look at map between spaces. For example, you can also look at maps between links. These are some kind of cobordisms between links. And now the result is that cobordisms between links give you maps between these spaces. So in other words, this invariant is functorial. Well, if you do it like I said here, you actually need to fix some signs because it's not completely functorial, but there are ways to do it. Okay, and before going to the odd world, I would like to just spend a bit of time looking a bit more in details at this TQFT. No, but the Euler characteristic is like the alternative sum of the dimension of the space in your complex, but it is the same thing as the graded dimension of your homology. So I want to spend a bit of time looking at this TQFT. So what it does, okay, so a collection of n circles, it associates the tensor product of n copy of A. And now to a pair of pens like this, that we call a merge, because I read it from bottom to top, so it takes two circles and merge them in one circle. You simply associate the multiplication of a polynomial algebra, because I remind you that A is just zx on x squared. To a split, so a reverse pair of pens, you associate this commultiplication here. And then you also have like a unit and a co-unit, but I don't need them for this talk, so we can forget about them for the moment. And now here, the main thing that I want to observe is that this functor is actually a symmetric monoidal functor. So this category of cobordism is a monoidal category if you equip it with just disjoint union. So you just take collection of circles and you put them side by side, and you take the cobordism and you put them side by side to the category of vector space with the usual tensor product. All right. So this is the usual construction. I think most of you already know it very well. If you have any question, don't hesitate to ask. Otherwise, we can go to the odd world. So what's the idea of odd Khovanov homology? Well, Ozsváth, Rasmussen and Szabó suggested this observation. When you apply f on a collection of n circles, what you really get is some polynomial algebra in n variable mod o xi squared. So this is some kind of symmetric thing where variable commutes. And so they suggested, what if we replace this by something antisymmetric, where variable anticommutes? So what happens if you associate to a collection of n circles an exterior algebra in n variables, and xi squared 0 is implicit here? Okay, so that's the idea of odd Khovanov homology. But wait, maybe you are thinking, a TQFT has codomain the category of vector space. And as vector space, these two guys here are exactly the same guy. So we have changed nothing. Well, yes, but the idea is now we are going to change the maps associated to the cobordism, and the way we will define these maps, we'll use this exterior algebra structure. So let's do this. So say we want to define the functor of on some cobordism W from a closed one manifold sigma 1 to a closed one manifold sigma 2. So we already know that it should go from an exterior algebra in number of components and sigma 1 variable to number of components in sigma 2. And we can just look at elementary cobordism, because all cobordism are like composition of them. So let's say we have a merge like this. So what I do is at first I will put some label for the components, because this label will tell me the name of the variable in my exterior algebra. And here I will assume that this pair of pants is inside a bigger cobordism, which is the identity everywhere else. And I identify the labels of the variable in sigma 1 and sigma 2 outside of this picture. Okay, now the observation is, if you take the quotient of this exterior algebra by A2 minus A1, you get something that is isomorphic to this exterior algebra simply by identifying either A1 or A2 with the variable A. This is quite easy to see. And so you can define the merge here as a composition of the projection and then this isomorphism. And so concretely here, what I'm doing is actually very easy. I just take an element, which is an exterior product of variable here, and whenever I see A1 or A2, I replace it by A. And this gives me an element there. This map just do this. And then we can look at a split. So now for the split, what we observe is that there is an isomorphism between this exterior algebra, where you have one less variable, and this guy here, which is you take your element in this exterior algebra and you somehow multiply on the left by this element. And this isomorphism sends A either to A2 or A1. And it is quite easy to see that it does not matter, because if you have A2 minus A1 times A1, this is just A2 times A1. And if you have A2 minus A1 times A2, this is minus A1 A2, which is the same as A1 A2 A1. So this is well defined and does not depend on this choice. And then you can embed. And so concretely what I'm saying here is that this map, what it does is you replace each occurrence of A by either A1 or A2, it does not matter. And then you multiply your whole exterior product on the left with A2 minus A1. And so here you can already see a difference with the usual case that I explained to you before, because here you multiply on the left. So somehow you need some global picture here. And I also would like to point something is that here we are making some choices, because we could exchange the role of A2 and A1. So we could have done A1 minus A2, but here it does not matter. However, if you do it here, you either get A2 minus A1 or A1 minus A2, which are not the same, they differ by a sign. So somehow it means that whenever you have a split, you need to make a choice. So this is a first hint that OF might not be really a TQFT. Maybe the domain should be not the usual cobordism, but something else. Moreover, you can also observe that this functor is sensitive, sorry, it's a mistake, I think, to exchange of critical points. So, for example, here, if you exchange the heads of these two saddles like this, and you do the computation, because of this equation here, you will see that you get a sign. So this means that definitely OF is not a TQFT, because it is not even well defined with usual cobordism. And Ozsváth, Rasmussen and Szabó called this some kind of projective TQFT. But I think we can do better. What we need is a notion of cobordism which would encode this phenomena. And one solution to do that is due to Putyra. And he say we can use chronological cobordisms. So what are these chronological cobordisms? Well, a chronological cobordism is a cobordism with a chronology. That is a framework function that separates critical points. Okay, I think I can explain this a bit more easily. So what it means is that your cobordism should be equipped with some morph function, some height function that will allow you to separate your saddles. So you cannot have like two saddles at the same height now. And also, these critical points carry an orientation that we will draw as an arrow. This is already the arrow that I drew over the split before. Good. And usually what we want to do is consider this chronological cobordism up to equivalence, which will now preserve the orientation and the order of the critical points. So that now you cannot exchange distant saddle points, so you don't have this behavior that is not well defined anymore. And so now you can have a functor that is well defined. Hooray. But wait, somehow here we are still missing something, because this functor is not monoidal. And the first issue is that, I mean, the category of chronological cobordism is not monoidal for the Dijon union. And the issue is exactly because you cannot exchange distant saddle points and distant critical points in general. And even if we suppose that it was monoidal for some structure, there is no hope that our functor would be monoidal, because when you exchange, when you apply it and you exchange distant saddles, you get a sign. So there is no hope to turn it into a monoidal functor, because monoidal functor would give you like a strict commutativity when you exchange distant morphisms. So what you need is a notion of monoidal functor that would what we can observe though is that if you think of this morphism here, this split, as carrying some degree, say degree 1, then this would be some kind of graded commutativity, like you have in a homology ring. So what you would need is a notion of monoidal category for things that are graded commutative. And one solution to do that is to use enriched monoidal category in the same spirit as monoidal supercategory as introduced by Brandon and Elias.
We have another question. Sorry, I'm scrolling up.
It is.
Is there some kind of cocycle that measures the defect of this being an honest TQFT?
What? I mean, when you do your cube of resolution, there will be one. I'm not sure if it makes sense in general to talk about.
So I'm not sure if Aaron just wrote yes to the question we're talking about. There's also some discussion going on in the group chat.
Okay.
Aaron, did you want to elaborate?
I'm looking at the chat. I mean, okay, so I would say that there are ways to compute the defect of being an honest TQFT, and I will explain this a bit more later, I think. But okay, I will tell you more about it later. Okay, so you need a notion of graded monoidal category or enriched monoidal category. So let me explain to you a bit how it works. So we consider our ground ring, okay, now as a Z-graded ring in degree 0, and I consider the category of graded module with the degree preserving map. So it is the usual abelian one. And this category is a symmetric monoidal category. when you equip it with the usual tensor product, where you just add the degree of the element. The symmetry now is given by this graded commutativity. So the way we can picture this is whenever I look at a tensor product of two elements, m and n, I want to think about them is some kind of right and left convention. So what it means here, if you look at the bottom of this picture, this is the tensor product of m and n. And because n is on the right, it should be first. So it's at the bottom because I read from bottom to top. And then you have m. So this is m tensor n. And then you apply your twist. So this is given by a crossing. You can pair your m and you end up in this picture. But this is not the tensor product of n then m, but of n by m, because now here n is below. So you need to pull it to the top. And now you are like commuting distant stuff, and so by the graded commutative rule, you put this sign depending on the degree of your element. And so this gives you a symmetric monoidal category. And whenever you have a symmetric monoidal category, you can make a notion of enriched monoidal category over it. And so what you do, you define it as the enriched category with an enriched bifunctor over the enriched tensor product of the category and a unit object respecting the usual condition of a monoidal category. And so concretely what this means is that the Hom space in your graded monoidal category are z-graded k-linear vector space, or space, because K could be just a ring. And the composition is compatible with this. And now the tensor product functor respects some kind of graded composition rule. Usually in a monoidal category, you would ask that the tensor product of two maps composed with the tensor product of two other maps is the same as if you first compose your map and then do the tensor product. By definition, basically, of a functor. A functor should be compatible between composition. But in this graded enriched case, you need to throw in the symmetry of the category on which you enrich. And so this symmetry here gives you this sign, basically. And again, there is a nice picture, diagrammatic way to think about it, using this convention of right and left. Because here on the left, you have this picture. So you start with the tensor product of f prime and g prime. So you put them on the bottom, and because g prime is on the right, it is below. And then you compose with f and g. And so because you read from bottom to top, composing is stacking above, so you get this. But here you first compose g and g prime, so you get this stack. And then you do the tensor product, so you put this one here. And you can see that if you just exchange the distant f prime and g, you can go from one picture to the other, and this gives you your sign. So basically, that is a graded monoidal category. Okay, let's look at an example. What we can do is look now at the category K big G mod. So it is a category again of the graded K module, but now you take all graded map. So your morphisms are finite sum of homogeneous map. And so of course this is KG mod linear. Another way to say it is that you just replace the Hom space with the internal Hom space of KG mod. And you can turn this into a graded monoidal category by keeping it with the graded tensor product. So on objects, you do the same thing as before. You just do the usual tensor product of graded space. But now you need to define what is the tensor product of two maps having some non-trivial degree. And so to do it, you apply the same rule as before. So if you apply f tensor g on some element m tensor n, it is the same as just, you define it as applying f on m times g on n, but adding this sign, because again, you need somehow to commute g and m. And just a fun fact here to observe is that this category is equipped with a grading shift functor. So it's a functor that shifts element up by 1. But now, and usually grading shift functor do nothing at the level of maps. But here, because your maps carry a degree, you also need to twist them. And we will use this kind of things next week, so I think it's nice to observe it already here. I also want to say that there is a notion of graded symmetry for graded monoidal category. And basically you do the same thing as for a symmetric monoidal category, except now that your collection of isomorphisms should be not natural, but graded natural. So they should commute with some signs depending on the degree of the maps you exchange, because again, graded commutativity. But it is not very important for what we are doing here. So if you're not comfortable with it, don't worry. And an example is, again, you can use the same symmetry as before, but on K big G mod. Okay. So now my goal is to turn this category of chronological cobordism into a graded monoidal category, so that our functor OF will become graded monoidal. So the first issue we have is that if you just do a disjunct union of chronological cobordism, you could end up with points at with critical point at the same height. So what you do is you use again this right and left convention. And so you put first your coordinate that is on the right below, and then the other one, you put it on the top. And then the next step is that you need to linearize this category, because you need KGMod and rich category. And also you want to add some relation, so that when you exchange distant saddles, especially when you exchange distant splits, you get a minus sign in order to match with our functor OF. So let's do this. So let's K out cob be the K-linear category, where you take just formal linear combination of chronological cobordism, and you throw in this collection of relation. So because OF is not sensitive, I don't know which one is the good word, to exchange of orientation of merge, you put this equality. But when you exchange the orientation of a split, you put a minus sign. And you have something similar for a cap. Then you have some kind of oriented unit and co-unit relation. And then, like I said, when you exchange distant saddles, you want to get a sign depending on the degree of the saddle. But wait, I haven't told you about the degree of cobordism. So what you do is you define the degree of a cobordism as the number of cap minus the number of splits. And then if you do this, you can see that if you commute to distant split, because they have degree -1, you will get a sign. And for example, here, if you again exchange distant split, you also get a sign, and this, for example, corresponds to the kind of a twisted co-associativity that I showed you before. And so if you do all this, you get this category K opt cop, and it becomes a graded, actually symmetric monoidal category when you equip it with the right and left union. And so let me call this the category of odd cobordism. And then this basically for free, you get that the functor OF become a graded symmetric monoidal functor, whose codomain now is this category K big G mod. And so all this means that now we can also somehow redefine or rethink the way we were thinking about our functor, because you can define it completely locally. So to a circle, now you just assign the same space as before, except that you think of x as in degree -1. And you put this formula for merge and split. And you can see that they basically coincide with the usual one, except that you put a minus sign here for the commultiplication. And you don't need to think about things globally, like multiplication on the left and so on, because all these signs are completely encoded in the fact that you end up in this graded monoidal category. And so all the signs are given by graded tensor product there, which I think is quite nice. Okay, maybe now you are thinking that this is a bit sad, because we have like a category for usual cobordism, and then we have this category for odd cobordism. Maybe it would be nice to have some category where you could apply both your usual functor f and your odd functor of. And there is a solution for that, and this is also due to Putyra. And what you can do is, instead of going to this linearized category of odd cobordism, you can turn the category of chronological cobordism into a monoidal two-category. One way to think about this is, usually a monoidal category, it is basically a two-category where you have just a single abstract object. And the home space of this single abstract object is your monoidal category. And now here, a monoidal two-category, also called a gray category, is just a three-category with a single abstract object. And if you want the home space of this abstract object, is your monoidal two-category. And so you can do this by adding some two morphism or three morphism, if you are in this picture, given by change of chronology. So these are diffeotopies of the frame morph function up to homotopy. So what you do is you throw in some new layer of maps that will encode the fact that you are basically exchanging distant saddles. And because you do it up to homotopy, if you, for example, exchange first here two saddles and then exchange them back, it is basically the same as if you have done nothing. So it is actually equal to the identity here. And so if you do that, you get a monoidal two-category. And you can do something similar, and you can turn the category of graded vector space into a monoidal two-category, where the two morphisms are now multiplication by scalars. And then you can view both f and f as monoidal two-functor, where the change of chronology are sent to invertible scalars. And in the case of f, all these scalars are just one, because you don't have signs. Good. I think it's kind of cool to know that it exists. But I will mainly use this category of odd cobordism because I think it's a bit simpler to use for most things. Okay, so now that we have all the tools we need, we can go and try to construct odd Khovanov homology. So again, you start with some link L having k crossing. And now the new thing is you choose an orientation for each of these crossing. So you just put an arrow that can go there in this direction or the other. And then again, when you have done that, you can resolve it into a 0 resolution or a 1 resolution for each state. And as before, you construct your cobordism by putting a saddles. And you just use this orientation omega to orientate your saddles. And so if you do this, you will end up with a huge cube of resolution where the edges are chronological cobordisms. However, there is an issue here. Because if you remember what I told you, in the even case, this cube was commutative. Because in the even case, you can exchange distant saddle points. But here, phase could commute or anticommute. Because for example, if the two saddle points you are exchanging are split, then you get a sign. So somehow you need to deal with it. And so for this, you define, what you can do is use a sign assignment. So what you do is for each edge of your cube, you choose a sign, plus or minus 1. And then from this, you can define a signed version of your cube of resolution when you just twist the edge by these signs. And one of the main results of Ozsváth, Rasmussen and Szabó is that basically, and here I'm not sure if they do it in general, but at least I know that what they do is they give you a way to make a choice of orientation omega such that there exists a sign assignment so that the cube of resolution is, the signed cube of resolution is anticommutative. But I know that Putyra showed that in general, given any orientation, there exists at least a sign assignment. And somehow here is the argument to do that is that indeed, if you look at your cube of resolution and you look at the the signs each phase has, this is basically a cocycle. And because your cube is contractible, this cocycle has to be a co-boundary. And this co-boundary gives you the sign, basically. That maybe this answers the question that I was asked before. Okay, and so it means that we can have like an orientation and a sign assignment such that we have an anticommutative cube, and so we can construct a complex by applying the odd functor on it. And now the result is that the homotopy type of this complex is a link invariant. And also, which is kind of nice, that it does not depend on the choice of orientation you have made, and it does not depend on the choice of sign. So you really have like a unique odd Khovanov homology. And then, okay, so maybe we can talk a bit what are the properties of this this odd Khovanov homology. Well, because the functor, the odd functor and the usual functor are equivalent modulo 2, because they just differ by some choice of sign, basically the complex are the same modulo 2 also. And moreover, again, the great characteristic of this odd Khovanov complex is the same as the joint polynomial. So you have like a different categorification of the joint polynomial. But wait, maybe you are thinking that maybe both these homology theory are the same. Well, it appears that it's not the fact they are distinct, because I know that Schumakovich has found some pair of links, such that, for example, usual Khovanov homology cannot distinguish them, but the odd version can, and vice versa. So there are really distinct link homology. So it is interesting. I don't remember what kind of link. I don't have the example. I think they are reasonable. Like, I don't know.
I want to say they're like 10 crossing or something, yes. But yeah.
I had something like this in mind, but I don't want it to take risk. Okay. And I think it's also worth mentioning that there exists a covering version, because you can do some kind of covering TQFT, and which encompass both of them. And this was done by Putyra. Okay. I wanted to say also something more. For people who know usual Khovanov homology, you probably know that there's also this construction due to Barnatan that allow you to not apply the TQFT, but work in some kind of quotient of the category of cobordism. So what you do is you look at the linear category of cobordism, and you throw in some relation, and then the homotopy type of the Khovanov complex inside this category of cobordism is already a link invariant. And it appears that you can do the same thing in the odd case, and the relations are basically the same, except that now the torus is sent to 0. Here you would expect that 2 in the usual case. And you can also do something similar with dotted chronological cobordism. Okay, and if you want to know more about this, you can look at Putyra's paper. Okay, so this was for links. So all this works really well for links. But now maybe we want to extend this to tangles. So let me try to sketch you quickly the construction, and we will go back on this next week. And I'll try to tell you what is the issue. Okay. Okay, I don't want to spend too much time explaining all this, but okay, basically what you can do is whenever you have a tangle, so now you have like, just like a link that is cut open, so you have like a starting point and ending point. What you can do is look at all the way you can close this tangle by this semi-arc diagram. So you look at all the way you can do this, and you will end up with some collection of links, basically. And then you can do this usual construction of even Khovanov homology or odd Khovanov homology. And of course, by construction, this will be a tangle invariant, because I mean it is invariant at the Rasmussen move by the result of Khovanov or Ozsváth, Rasmussen and Szabó. But no, the thing is, one fundamental feature of tangles is that you can compose them. So whenever you have two tangles with the same number of ending point and starting point, you can just glue them together and get a bigger tangle. And somehow you would like to also see this at the level of the invariant. So when you can compose two tangles, you would like to be able to relate the complex you get from one tangle, the other, and the composition. And so usually what you do, don't focus on the details, but usually what you do is you construct something that we call an arc algebra. And to this space here that you got, so the space you associate to tangles, you give it a structure of a bimodules over this algebra. And so now to tangles you associate a bimodule. And the thing is, so when you have two such bimodule, you can tensorize them over this arc algebra. And now it appears that in the even case, if you tensorize the bimodule of one tangle with the bimodule of another tangle over this arc algebra, you get something that is isomorphic to the bimodule you get if you have composed the tangles. So that is the way we want to relate composition of tangle with the invariant. Now the issue is, if you try to do this for the odd arc algebra, so the algebra that would construct exactly in the same way as in the even Khovanov homology, but using the odd QFT instead of the usual one, you get a non-associative algebra. And next week I will explain this diagram and why. And then, because you have something non-associative, there is no way you can define what it means to take the tensor product over a non-associative algebra. Well, as far as I know, there is no way to do it. And so you are stuck, because you cannot do something like this in the odd case. So next week, I want to explain to you how to construct a framework so that this odd arc algebra and the bimodule you get for tangles become somehow associative by changing the monoidal category in which we work. So if you want to know more about this, please come next week. And because I'm almost out of time, I think I will stop here with this motivation for next week.
Thank you. Let's thank the speaker. Okay, so we're going to keep recording for the next 10 minutes. Are there any questions? If you have any, just unmute yourself and ask your question.
Yeah, I have a question. So it seems like these two theories correspond to two choices of Frobenius superalgebra, where you've taken kx mod x squared, where x is declared to be even, or degree 0, and then kx mod x squared, where x is declared to be degree 1. Can you, how much of this theory goes through for an arbitrary supercommutative Frobenius superalgebra?
If I remember correctly, I think Putyra has some characterization that you need for this Frobenius algebra so that you get like a link invariant. Please correct me if I'm wrong, Chris.
Yeah, just like in Barnaton's story for Khovanov homology, the Frobenius algebra has to be two-dimensional. That's like just to prove invariance. And then you have other conditions that get imposed by proving link invariance. But the first major restriction is that it's stuck to be two-dimensional because of the circle.
I see.
And then Krzysztof can explain more. I mean, he's the expert.
So Chris said every rank 2 super Frobenius algebra gives an invariant.
Is there some intuitive explanation for why this thing has to be rank 2?
Is it just that there are 2 resolutions, or is that the wrong way to?
I feel like both the 2-ness and the 2 resolutions have to do with the fact that you're doing an SL2 theory. For SLN, there's a multi-term resolution.
But there are no like odd SLN homology.
Yeah, and I think the two-dimensional is also related to, you want the dimension of the, I mean, you're trying to categorize, like Elias was saying, the circle, you're doing SL2 theory, so the circle is supposed to evaluate to Q plus Q inverse. So you want the space of maps from the empty into the circle to be two-dimensional, and that's part of why the Frobenius algebra ends up being two-dimensional. Well, I mean, that is why I think.
There are, SLN theories, but you need to have more interesting forms, so not just cobordisms, but forms in order to recover such theories.
I see.
So I'm totally not up to date. This is Dror Barnatan. But one reason to switch to tangles was because you could then divide and conquer and compute more quickly. Does your switch to tangles allow it for the odd Khovanov homology?
I'm not really aware of the techniques that you can use to compute usual tangle homology like this. But I mean, in theory, our solution could be put into a computer, but I don't think it will be very efficient because somehow computing the signs that will appear is not easy.
Easy and efficient are different things.
Yes. But I mean, I should probably first look at what kind of algorithm are used in the even case to see if they could be extended in the odd case.
Okay, thank you.
So yeah, okay. I mean, my answer is that it's definitely possible to put it into a computer, but I'm not sure if it will be quick.
No, so for example, just yesterday, I was looking at the paper by Lisa Picirillo, where she uses some computation for a very large knot in order to derive something about the Conway knot. But the point is that she had to compute something for a knot with 30-something crossings, or I don't remember exactly how many, but a large number. And if you had to consider 2 to the 30 smoothings, you'd die. And the point is that you don't have to in the case of ordinary Khovanov homology, but do you have to do it in the case of Khovanov homology? Yes, so Krzysztof says that it should work. Well, good.
But I mean, somehow computing the complex for like a small tangle is easy, I think. But I'm not sure if maybe there could be some issue with the gluing. Because when you glue, you need to compute the signs, and there I'm not sure if there are.
So Ben Cooper has a question in the chat. Have there been any computations of universal odd Khovanov, writing 1 tangles as indecomposable modules over the Frobenius algebra in this context?
Wait, so when you mean a 1 tangle, it is which one? Just like you go from 1 point to 1 point, or 2 point to 2 point?
1 point to 1 point, I think.
Not as far as I know, because we haven't really worked with the generalized or arc algebra, actually. So we just work with like even endpoint. So with 1 tangle.
So I think, Calvin, I think there's like the tangle version for the Alexander polynomial is like not Floer homology tangle Floer homology, and that does have a UQ GL11 action. And it's the same sort of oddness here. There's just like a Lie superalgebra acting there. I think it might still be a conjecture that not Floer homology itself has a GL11 action.
I remember reading that homology is related to some categorification of OSP12. I don't know if like an explicit to action from the categorification of OSP12 was done.
Okay, so I think the questions are still coming. I'm just going to pause the recording. So let's thank the speaker again, and then we will continue just hanging out and asking questions.
Thank you for listening.